Hello, everyone. Today we're going to talk about doing large-scale analysis on smart contracts, basically blockchain scale, where we take all the contracts that are deployed on certain blockchain, for example, Ethereum mainnet, and we try to do data analysis and vulnerability analysis on all these contracts. The purpose is to do it for fun and profit, hopefully both. But yeah, let's see how it goes. So who I am, my name is Vahe. I'm CTO and co-founder at Hexens. You can also find me in Twitter by nickname Cameo. So what we do at Hexens, we do cybersecurity and blockchain with a holistic approach. So we do provide code review services. Sorry. So we do provide code review services and penetration testing services, but not only that, we're also developing tooling. And one of the tools that we developed, we used for this presentation to collect all this information. My background is in CTFs. I'm a big fan of capture the flag events, and also I did not just start from blockchain security, like general cybersecurity background, doing Web 2. We don't call it Web 2 in Web 2, but yeah, now we call it Web 2. Yeah, so nice to meet you all. So let's start. So today we're going to analyze contracts on Ethereum mainnet. We can do it on for any kind of EVM like chain, but I think the mainnet is kind of like the most important, where you would want to start from. So a little bit of general statistics about Ethereum mainnet. So there's around 68 million contracts deployed, but these are like total deployed with bytecodes, like duplicated bytecodes. A lot of stuff, as you know, just duplicates on chains, for example, I don't know, Uniswap pairs, and etc. And out of this, total verified amount is 704,000 contracts. So we will be interested in analyzing those, because arguably those are most likely the ones that you would care about. And also this gives you ability to analyze deeper the contracts, not only on bytecode level, which where you do miss a lot of metadata about the code, about the contract itself, like contract names, sometimes function names, if you cannot rainbow table the selectors. So out of this almost 700,000 contracts, like more than 95% are Solidity, which is kind of obvious. The biggest parts of the rest belongs to Viper, and the other ones are pretty much negligible. They're to like not a lot of contracts on Ethereum mainnet on other languages. So how you can do this kind of stuff, how you can do a large scale analysis on contracts. So we developed a tool called Glider. This is a query framework for smart contracts. The way it works is that we kind of create the specialized artifacts out of the contracts, and we put them into a database, and we give you a framework to work with this database to query for stuff, to analyze it, to do complex analysis. So the biggest thing, like difference between this and other, let's say, program analysis tools that you can find for smart contracts, is that Glider treats code as data, which gives you the possibility to do this on scale, right? If you just run a program analysis tool on millions of contracts, most likely it's not the best decision to do. But if you kind of structure it as data and you work with it as you would work, let's say, with the database, and this gives you the scalability. And also another great thing that it adds is that you can write your queries in a declarative fashion, which is arguably way easier than just writing imperative code. So you can see like a short example of Glide, where we have this declarative chain of calls, like functions with one of the properties public or external, with argument type, level down to the instructions. We say, give me the balance of, next instruction, transfer from, next instruction, balance of. So yeah, I'll talk about Glider in between when I will be showing you some vulnerabilities also. But let's start with the fun part, where we used Glider to analyze some of the just I don't know, weird or crazy statistics on chain. So we used the Glider to find the longest contract name, which is basically like 240 characters, which is basically just the monologue from quite a famous meme, the woman on a plane or whatever the meme is called. I don't even remember all the stuff here, but apparently someone just remembered all this and created a contract. And the funny thing is that this length of the contract name was actually, I think the author would go even for a longer name. Is that this they were limited by the ext4 file system file name, which is 255 characters, and I guess that was the reason why they stopped at some point and not went even further with the name. So there's also, so for the contracts it's even smaller, but like we found the longest function name. It's 2,000, almost 2,500 characters, which is this crazy contract with a name of dollars, just dollar symbols, and the function is dollar symbol and underlines for 2,500 times, and it just transfer 1 Ethereum if you call it for some reason. Longest modifier name, which is a nice example how you can keep your naming conventions. Just the modifier name explains everything that the modifier does, like detect bot transaction, then register transaction, execute cron job after. So you read it and you understand what it does. A nice example. Longest variable name, this is from the same contract. And one thing that was interesting to check out, like what's the deepest mapping used? So how many keys? And we found it, and it's called 6 combo, and it uses 7 keys. So you would need like 7 key dereferences to get to your unit right out of the right corner. Yeah. So yeah, some crazy things going on when you analyze contracts by millions. Some interesting statistics on the compiler leaderboard, as we can collect this information as well. As you can see that from the top 10, it was something that you would expect. The 0.8 version is the most used, but 0.817 is just like top one, with over 12% of all the contracts deployed are compiled by 0.817. One would think that maybe there is a need to do some correlations on this. I can just say that 0.817 was released on, I think, September 2022. So maybe it's somehow correlated with all the capital deployed during the DeFi summer and when the projects finished developing and a lot of projects shipped. And maybe that's the reason why the 0.817 is actually the most popular compiler used. Also an interesting thing, the 0.424 is in the top 10 also. So not something that you would expect. It's too old, but there's a lot of contracts with 0.424. They go 3.5% almost. And the bottom 10, of course, like the worst, not the worst, but the least used compiler is 0.63. I can say from auditing experience, it's really like, this is something that you would like, it's really connects with the, let's say, with the fact that I rarely seen contracts with 0.6 compiler for some reason. It's hard to say what's the exact reason, but yeah, it's usually 0.7, 0.8. If you do something old, it's 0.4. So let's do some compliance tests, right? So what kind of ERC compliant contracts are out there? Of course, the most popular contracts are ERC20s. There's 290,000 contracts out of this 700. contracts, 700K contracts that are just tokens, like ERC20 tokens, which is 43%. Out of which, so it was interesting to check whether how many of them uses the permit functionality. So so with Glider you can check for what kind of functions are being used, called. So what's the inheritance hierarchy, how the code behaves. So we used all this functionality to kind of try to find the best, let's say, the best way how to validate that this token is ERC20, which is basically just we open the ERC20 EIP20 draft, and we just looked at what contract should have to be compliant. We just formalized it with Glider Current. We found all the contracts. So it's not that we searched with the, let's say, contract name ERC20. It will give you some nice results, but you will miss a lot of other stuff as well. So not a lot of permits. Only less than 3% of the contracts, like all the tokens, ERC20 tokens, use permit functionality. The second one, obviously, is ERC721, the NFTs. There are 59,000 of them, and it's almost 9% of all the contracts deployed on Ethereum mainnet. We also remembered about vaults, like for 4626. As you would think that there are a lot of them, but there are not too many of them if we don't take in account some duplicates. But let's say from a project perspective, it's not too many projects using defaults. Like it's 1,158. Just as an absolute number, like it's not small, but in correlation with NFTs and tokens, it does not look so big. So it's 0.17% of contracts. And we also looked for 777s. This is connected with one of the bugs that we will talk about further in slides. Very few, 253. But an interesting thing about these tokens is that there are few. There are a lot of like high volume ones, like IMBTC, which has a lot of volume. So an interesting thing that shows that actually this slide shows is that more than half of the contracts on Ethereum, the dominating part, are just ERC20 and NFT tokens. It's like 52%. So I don't know if that's good or bad, but that's the statistics. Let's talk about something that is called libraries in Solidity, and how were there adopted any anomalies with contracts with libraries. So in general, using libraries turned out to be a really very adopted approach, as 80%, more than 80% of contracts use libraries, and this or that way. It might be the safe math. It might be, I don't know, so safe transfer. So that there might be safe ERC20. There might be like different kind of libraries used, but in general, like more than 80% of contracts do use libraries. This looks like a success for libraries, and looks like people do really need them. Some anomalies. The contract with the most number of libraries used, it was like 109 libraries. So if you open, this is from a project called Rainlang. You can check with the contract name if you want to try find it, or you can try to find it by the contract address. So I think it was something like an automated contract generation. Maybe that's the reason it generated 109 libraries. But if you open up the Etherscan page with this contract and you go to the contract tab, it will be like almost infinite scrolling down to find to see all the source code. That there's so many libraries used there. So that's the world record at least for Ethereum mainnet, is 109 libraries used in one contract. So deployed libraries, not that well adopted, only 5,600, almost 700 deployed libraries, which makes like 0.85% of all the libraries used. So there's a lot of interesting and crazy stuff you can find if you look for let's say millions of contracts. If you search within millions of contracts. So one thing that we thought is like it would be really fun to take a look how many of the contracts are using debugging in production, which is we just try to find the console log calls on the deployed production code on the Ethereum mainnet. So 4,000, almost 900 contracts they did deploy with the console logs turned on. It's 0.72%, out of which almost all of them, like the major part of them, is hardhat. We're using hardhat, it's like 76%, and 6.5%, around 6.5, used the Forge. And the rest used maybe some custom console logs, or they changed, or they just copied and let's say implemented it directly inside their contracts. So when looking at the contracts, we found that there are a lot of cases where people just forget that this information will be visible for everyone. Let's say when verifying the contracts, you can actually kind of show your full path. You can do like full path disclosure on your local files or whatever. Or just let's say sending to remappings JSON. So you can see, we say hello Dave, as Dave showed us all his folder structure where he keeps all his contract files and etc. And it turned out that Dave is not alone. There are almost 7,000 contracts exposing like their full path disclosure to anyone. You can just check like what kind of username they have, what's the folder structure, so partially folder structure. This is not a big deal in a sense, but you can see we found something very interesting. We found someone called Safu deploying a contract and forgetting about full path disclosure. So I guess your funds are Safu with him. So let's talk a little bit about the whale contracts. One would think that it might be obvious who has the most contracts on the chain, and it starts with buy but does not end with nonce. It's Bitstamp. This is interesting because I guess I'm not even sure if they're operating right now, the Bitstamp. But the thing is that so they have a lot of duplicate contracts. So there's one contract with 22K duplicates, which is a lot, but not like, we've seen way more. Second one is like 230,000 duplicates, which is almost around the Uniswap pairs, like V2 pairs, which one would think has the most duplicates, but no, because Bitstamp has a contract, like a deposit contract, which has more than 10 million duplicates. So this contract was used as a deposit contract. Let's say when you, as far as I understand, when you opened an account on Bitstamp, instead of just giving, let's say, a managed private key and creating an EOA wallet, they used the deposit contracts, and for each user they deployed the deposit contract. And this was done like way back ago when Ethereum was way cheaper, the gas was not so expensive. So apparently they had the money to do this. But the crazy thing of that is it's like 15.3% of all the contracts deployed, like out of the 68 million, just belongs to Bitstamp, which are like not even used right now, as far as I'm concerned. Okay, so this was some of the fun part. let's take let's start talking about a bit more serious things, how you can find some real vulnerabilities on scale, and maybe even get some rewards. So this, let's call it for profit section, but honestly, I think it's both. Like it's both for fun and profit, and also it's useful for projects as well, and helpful. So what is the most important thing when you will try to hunt for bugs on scale? Is that let's say you have an idea about the bug, something that you maybe found during an audit, or something that you just read about, some bug that you read about in some other audit report, or maybe in an article, or you just woke up and you just thought, okay, if contract does this, it looks like it's vulnerable. Is there any vulnerable contracts out there? So you can use Glider to find all these contracts, and I guess that's, yeah, like you can use it as a data tool. It's not only about fun. You can do some data analysis that is also very impactful. But as being a security minded person myself, I see Glider more as a security tool, where you can describe a vulnerability, query for it on the millions of contracts. And the most important thing where you should start is the formalization of the bug. So you know about the bug, so when you think about the bug, you think of it with, like, let's say, using words, right, and ideas. But the computer and the query cannot understand your ideas. So you need to put your idea of a bug some way in a way that is manageable by computer, let's say. So that's called the formalization of the bug. So it starts like, what are the requirements of the attack vector? Can you formalize them? What are the blockers? Like how you can eliminate false positives, and also formalization. Like there's a, let's say, there's a line up to which you need to formalize. So don't overdo it, and it's better to have, let's say, a dozen of sharpened queries that have really great true to false positive ratio, then one very generic query that will try to include all the let's say all the branches of the possible attack vectors, but also will generate a lot of false positive. And when there's a lot of false positives, there's basically it becomes the bigger the number of the false positives, the more useless will be the query, let's say. So we'll start with the most obvious one, with the self-destructs. So is there any contracts that anyone can call and self-destruct? So we know about the bug. So that's how the bug sounds inside your brain, most likely something like that. But we need to formalize it to query for it, right? So what's the purpose of finding this? It's obvious with this bug. You can break the contract, and you can also steal all the ether around the contract, right? So how you can formalize it? So, and this is an example how you can do this. For example, with self-destructs, and as further we will be formalizing more complex vulnerabilities. So we try doing this. We say self-destruct should be inside a public or external function, but this is not a strict requirement, I think, as if it's even in an internal function, most likely there's a way how it's reachable from public or external. But like this eliminates a lot of just going more, as I said, like doing more sharp things will give you better results. And you can just do one query that finds in public and externals, and think of another one that will try find some other attack vectors. So obviously you should call the self-destruct. That's the second requirement. We also want the self-destruct argument, the address that you're self-destructing to be controllable by the caller, by the attacker. So as for example, if you can call the contract, but it always self-destructs, let's say, to predefined address, yeah, the impact, there still will be some impact, as you can, let's say, break the contract, just self-destruct it, and it may break some logic on some other contracts that rely on him, but at least there is no let's say ether incentive to actually do this. You will not get the balance of the contract. So we want to only include those self-destructs where we can control the address. And when I say controlling the address, this is also something not formalized. To be more precise on this, I would say that we need to do the data flow analysis on this argument, and we check if it's so do other like tainting or maybe just traverse the data flow and understand if it's dependent on some variables that are controllable by the attacker, which are, let's say, a message sender. Okay, it's controllable by the attacker. The external arguments of like the arguments of the function, like external or public function, they are controllable by the attacker. So you don't need to understand how data flow works. You don't even really need to know what data flow is to use the functions that Glider gives. So it abstracts all the stuff that you need to know about the data flow. You can just call, let's say, a backward df function on the argument of the self-destruct. It will give you all the dependent variables that this argument is dependent on, and you can check like whether it's something that caller can control. Okay, and you don't even need to do anything manually. There are functions that you can call that will just give you true false if it's controlled by the attacker or not. So there's an optional thing which you can use in your formalizations. There should not be a check on message sender. Let's say there should be no if plus revert structures where message sender is part of the condition. There should not be any require and answer call where the message sender is a part of the condition. Okay, so this is, as maybe you can call the self-destruct and you can control the address where it's self-destructing to, but you don't want the cases where there's the call has an authorization mechanism, right? Let's say it's only owner or anything like that. So we want to get rid of this kind of stuff. So running this formalized query with which does include this optional field as well. So we found exactly 160 contracts. As you can see, some examples like there's a release function which self-destruct to message senders, a contract called B that has a function, a contract called C, sorry, with a function called B that self-destructs it. So there's a little bit more obvious names like kill. This one has a nice check that says like the if balance equals 0, only then it should be self-destructed. This kind of thing show that you might need more iterations on your query, right? So there's something you might formalize something, and then run the query, you can see the results, and then based on the results, you may decide to iterate a bit more and add some additional requirements or constraints to your query. I'm showing you all this because all these contracts are already dead, so no one can actually exploit them. Query was really short. They took like 50 lines of code, and yeah, so it's basically just a reference to Cyrex fatality when it explodes himself. So it's pretty much the same here. So all these contracts already were self-destructed, but the code was out there, so you can still analyze them. So this one was not this example was not about the profit part, but this was about the, maybe, let's say, like it was us trying to see like how obvious things can work, and like they did work, but like you can find the contracts, but they're dead already, so you're just a bit late on them. So yeah, no profit with this ones. But let's see what's going on with the next vulnerability. So Something that maybe some of you know, some of you don't know. There's an ERC. There's a tricky ERC 777 reentrancy based on read. So like reading balance of a token. So this is an example code function called swap, where we obviously swap some tokens, and usually you can see this kind of patterns for the for the contracts that are trying to work with fee on transfer or trying to count the fee on transfer tokens is when they call a balance off on address this, just to check what's the balance for that token right now. Then they do the safe transfer from transferring the message sender tokens to the current contract, and then they call balance off once more to kind of see, okay, what's the actual amount of tokens received. Usually just subtracts from the balance before, and the amount that you get gets credited to your balance or something like that. So that this will be this second balance of subtracted from balance before will be the amount that you most likely will be credited. So and the trick is that if you're dealing with ERC 777 contracts, there's a thing called so let's open the EIP 777 and see like why it's important for this case is because so one of the things that 777 tokens need to implement is a call to a function called tokens to send if the holder of the tokens has registered ERC 777 token sender implementation. So there's a registry contract which is I think described in your EIP 1820, where if you're dealing with this kind of tokens, anyone can go and register different kind of implementers for their address. So one of the types is token sender, and if you do register this, then token contract, whenever you are sending any kind of tokens, like any amount of tokens to some other address, the token contract will call a tokens to send hook. And the tokens to send hook is not a static call, is not something like it's just an external call which basically gives you ability to hijack the execution. If we go back here, so what will happen is you will call the balance off. So the contract will call the balance off, then it will call the safe transfer for your address, and if you did register the operator, it will call a special hook function on whatever address you have mentioned in the registry. So basically you can re-enter inside this line. Okay, so let's see why it's important for an attacker. So this structure, I think, will show you this a bit better. So the first thing for the attack is that the attacker needs to register himself in 1820 register contract as his own. Let's say as his own. He can give some other address. It's not important. So as his own ERC token sender. So then when he calls the swap, well, let's see what happens. So there's a balance before, which sets the balance before to 0. Let's say it's the first, like the contract does not have any balance, right? So balance before equals 0, then the safe transfer from call happens, and we re-enter here given this EIP 777 feature, and we call the swap once more. So we re-enter before sending the actual amount. So the thing is that like if you the 777 token will call your hook before actually sending the tokens, right? So you re-enter into swap function, and you still have tokens by yourself. So there's one more balance off, which puts the balance off to 0 in this internal call, and on the second one only, you do send the tokens. You really send the amount of tokens that you wanted. Let's say, I don't know, like 1 million tokens. Then this transferred dx variable will get the amount that you actually used. Let's say 1 million tokens, and then it exits this internal call, goes back to the first level of reentrancy, so the original call. And here, as you registered your balance before to 0 priorly, you will still be credited the same amount of tokens, let's say 1 million. So you basically just multiplied by 2 your amount that you wanted to be, let's say, deposited, swapped, or whatever. And this is even better than just double spending, as the more levels to this reentrancy, the bigger the multiplier is. It's basically equals the levels of reentrancy. If there's 2 levels, then it's twice as more, let's say, tokens. If it's 10 levels, then it's more than, like, it's 10 times more tokens. This is something really, this kind of pattern you can find in bridges, and it's quite popular to use the fee and transfer counting there. So obviously, this can be mitigated, right? If you just have a non-reentrancy like modifier, or any kind of other reentrancy blocker modifier, or I don't know, function calls, this can break the attack, obviously. And another way, also an interesting way, if you don't really want to just have a reentrancy modifier, and your only concern is the ERC 777 reentrancies, is to have a require call that the amount that you got after subtraction is lower or equal to the amount that is being set in the call by the argument that is controlled by the caller. So here, if we go back, so this dx variable or argument is the number of tokens that you transfer. You can see here, if you add a require call that this transfer dx is lower or equal to this dx, so it will actually break the attack vector. You cannot attack this contract. So okay, how should we formalize this, right? So we should have 3 subsequent calls to balance off transfer from, or maybe safe transfer from, which is pretty much the same, and 1 more balance off, and they all should be done on the same target. So basically the same address, right? It should be the same token that you call the balance off, transfer from, balance off. The second thing is that the target needs to be controlled by a function argument. Yeah, so I need to be, so I need the situations where I'm saying the contract, I'm telling the contract which token I'm trying to transfer. So there should be no check for the subtracted amount, and also there should be no reentrancy blockers. And a thing that is hard to check, and this is most likely will be done outside of the query, is you should check that contract is accepting ERC 777s or not. Okay, does it work with this kind of tokens or not? So this is hard to check with the, right now at least, it's hard to check with the inside the glider, but you can get the results, and you can check it by just manually or using some other scripts. So we got over 500 vulnerable contracts. Unfortunately, most of them did not accept ERC 777s, even though they were vulnerable. As you can see here on the right side, there's some example of the outputs. Obviously, we will not be showing you some real ones that have vulnerabilities right now. It's either already dead contracts or something that blocks you from the contract. For example, this is there is an only smart yield modifier, so that's why I told you maybe situations where you need to reiterate on the query. Let's say add a logic that checks that the call is not authorized, right? So anyone can call it. So that's an example. But luckily, we did find the vulnerability on one of quite famous bridges, and we did get a nice reward for this finding. I decided not to include the names of the projects here, but you can reach out to me and I can give you more information on the case. So this was not luckily it was not the only case that me or our internal team have found some bugs that gave us a payout. So there's another example of what kind of stuff you can check with Glider. So is the uninitialized implementation. So let's start with the bug itself, right? So what's the problem with the uninitialized implementation? So everybody knows most likely about the proxy implementation pattern. That's for the upgradability of the contracts. So the implementation contract usually holds the logic and it holds the storage layout, while the proxy contracts hold the implementation address. In most of the cases, of course, it holds the implementation address, forwards messages to the implementation, holds the actual values of the storage. They should call the initialize function on the implementation, as we don't have the usual constructor logic for the implementation. And also we usually include the upgradability logic, although that's different because there's transparent and UPS proxies, so it may differ. So in terms of, let's say, from the developer and security engineer perspective, it's pretty obvious that whenever you deploy a proxy and implementation, you should call the initialize function on proxy as soon as possible. Ideally, just in the transaction where you do deploy it, or maybe have some let's say logic that blocks non-deployer addresses to call this initialize function. But like everybody knows, you need to call the initialize, right? If you don't call it, then I can call the initialize. I can set all the important variables, storage variables, to the values that I want to, and basically most likely take over the contract, right? So and given that the actual storage values are not in the implementation but in the proxy, so the question is it really that scary to forget to call the initialize function on the implementation contract? So yeah, you need to call it on proxy, but like, should you also call it always on implementation? And like ideally yes, but like on most cases it's safe, it's not scary, unless there is a delegate call to a non-constant address, so to address that you may be able to control. So this so some of the queries that I tell you about. So we for example, this was done before the IP that blocked the way how they changed the way how the self-destruct works, when it just pretty much works like as a sendle. And back in like early this year, when this bug was being analyzed by a team of engineers, so it was still, you will still destroying the contract, destroying the, let's say, bytecode of the contract, right? So, and that's the thing. So if you have a delegate call to a non-constant address, which most likely can be controlled by the owner, right? This address, you can delegate call to a contract that self-destructs, and basically self-destruct this implementation contract. And this can be crucial because if you destroy the implementation contract, for example, for some proxies, it will be, let's say, the UUPS proxies. They will not be able even to upgrade the implementation. It will be bricked. And also, there's another scenario where it can be also really very critical. It can have really very critical impact. Is when, let's say, this contract is being used in some other contracts are calling to this contract with some verifying functions, and that will be crucial as well if you destroy this contract. Let's see a small example like of this proxy and implementation. So let's say we have an initialize function in the implementation. It has this initializer modifier. That's nice. And it's, so the important part here is we can see that we have like ownable init call here, which basically will set the caller as the owner of the contract. And most likely the delegate call that we want to, the address that we're delegating to, most likely it will be controlled from the owner, right? So if you don't have like another vulnerability of this setter being unauthorized. So I can call this initialize function as an attacker. I can call this on the implementation. It will not change anything for the proxy, obviously, but it will change for the implementation. I can change I can take over the ownership. I can call to I can do a delegate call to my contract, which self-destruct the implementation and break everything for the proxy, right? So yeah, here's the breakdown of the attack: call initialize function, take over the ownership, change the authorized target of the delegate call to a self-destruct, break the contract, and also get 3 successful calls. So that's what I meant. So let's say we have an example like this. Let's say there's another contract which is calling to our contract that is self-destructed. And let's say it's something like, okay, there's a pseudocode like guard, check, caller, message sender. And there's some checks that we need to do to understand if this message sender is authorized to do something. So you will get a free call here, and you can just bypass all this kind of checks. So that's the bad part. It's not only breaking the contract; it can also become like really like funds draining attack. So the way to mitigate it, and this is important for our formalization step, we need to understand how this kind of stuff can be mitigated, so we can get rid of the false positives, right? So there's 2 ways how you can do this. Actually 3. So 2, let's say, common ways and 1 custom. You need to add modifier, initializer modifier to the constructor from the OZ library, or you can directly call underline disable initializer function inside the constructor. So you need to do this to one of these 2 things with your constructor to block it. And the third thing is just basically emulate whatever does this modifier and this call, and just do it customly, maybe with some other function or something like, I don't know, some other storage values. And that's it. So how we can formalize this, okay? How we can formalize this attack, how we can search for it on millions of contracts. So we need to, so the first thing is this is also a nice example of this, let's say, problem of formalization. So we're talking about proxy and implementations, right? And we will be looking for some bugs in the implementation. But like, yeah, talking about this, it's obvious. If you look at the contract, you can understand that this contract, well, with very high probability, that this contract looks like an implementation, because it has like initialize function, or maybe it will have some other function that you understand that works like initializer. But from the machine perspective, from the, let's say, computer perspective, this is not a formalization. It does not know like what's the implementation contract. So if you want to find the implementation contracts, you need to formalize this somehow. And actually, it turned out that like the stats that we've seen showed us that the most obvious way was the best way. Actually, is just to find all the contracts that use that have initialized function, right? So for all this contracts that have initialized functions, it turned out there is no, like, literally 0 false positives, in a sense that some of them were not implementations and we found something else. Now, if you combine this with a couple of checks, you'll get a very high precision results, but we may let's say miss some of the true positives, right? So maybe the function was not called initialize, it was called initialize state or whatever. So yeah, this is a bit hard to, in this kind of cases, it is a bit hard to find all this cases with just 1 query. So better to shard it, as I said, and just write 1 query doing it work really great, and just have, like, I don't know, 5 or 6 querying to cover all the attack scenarios. So yeah, so the combined way is to find the initialize to find the initialize functions, and to check that there is an initializer modifier. So these 2 checks gives us really very high precision. I think we had like 0 false positives in terms of whether a contract is implementation or not. So there's a couple of other things that we need to check, right, for the attack. So we must have a delegate call, and this reduces the amount of the results like drastically. there are not too many implementation contracts that have delegate calls. But yeah, we need to check. It should have delegate calls, and the address that is being called, the target or the qualifier, let's say, of the call should be non-constant, immutable. So not a constant and not an immutable address. So another thing that we need to check is for the mitigations, right? So it either the contract should not have any constructor, which will be great. Okay, there's no way you can mitigate this, or if it does have the constructor, it should not have the initializer modifier or the disable initializer function called inside it. Yeah, and the third one, which you cannot actually do with Glider right now, is like you should check that nobody called this initialized function before, right? It's pretty obvious. So, but we'll talk about this last point a bit later. So if you formalize this, you run the query, you will get 436 results on Ethereum mainnet only. So they were, after eliminating some false positives, not in terms of the attack, but in terms of that they're old, they're dead, and they're already initialized. So there were 5 valid reports, and this also brought some nice payouts for the engineers who found this. So yeah, and about this last point on the initial on being initialized or not, if you open up the Glider interface, if you have some output, there's a nice button called like download as JSON. You can download your output as a JSON, and you can basically fit it to any kind of custom script that you want. Okay, so another attack, okay, that was really successful was the delegation attack. So let's imagine a scenario where a contract overrides delegates function to return the account if it's not delegated. So basically checking if it's delegated to, let's say, address 0, which means kind of not delegated, then it just returns itself. Okay. And if you have this situation and you also have the delegate and delegate by signature functions, and they do not check that the account does not equal to 0 before proceeding, then it might get really nasty. You can delegate, you can basically burn the voting power, as you can delegate to 0, but the delegate will still be set to the account. Okay, so I think it's not like that hard to formalize. The last couple of attack vectors were way more harder to formalize. But let's see how you can approach this vulnerability. So the argument of the delegate function should flow to an if instruction, and then like the condition, there should be a condition check that some mapping variable should be equal to address 0, and also it should have an instruction that returns the account. Okay, so this how we will check for this part. If delegates account equals address 0, return account. Okay, condition check for mapping to be equal. Yeah, so that's the first part. And the second part, we need to check that the function that call underline delegate must not have checks for address 0, right? So formalizing this, we got like 122 vulnerabilities with a bunch of reports and a bunch of payouts for. So this last couple of let's say vulnerability like attack scenarios that we someone from our internal team or me or anyone else who researched, they were successful. As it helped out the projects, real projects. It also helped the hunters to get payouts. So yeah, and also you can have way bigger confidence that, let's say, if you know about some bug and you checked it, you can be way more confident if you query for it and you can see the results, that you pretty much try to find everything, like everyone who's vulnerable. So yeah, but I mean, there's so much stuff that was not included into the presentation. So much stuff that you can have on your mind and check it out. There's still plenty to research. Like there's a lot of easy recover bugs. There are other kind of reentrancies, return bugs, compiler bugs, unprotected callback. This is a funny thing. So you might think that, okay, it's too obvious that you need to protect your callback, let's say Uniswap callbacks. But like if you, so the funny thing is that when you deal with the millions of contracts, a lot of crazy stuff can happen. Like if you feel, if you think that they're like, any kind of developer will put let's say an authorization mechanism for callbacks or for whatever. Now it's not the case if you deal with millions of contracts. You can find like a dozen of contracts that just don't implement that they have that they can have even the most obvious bugs there. Of course, this kind of things is super useful for like third web-like incidents where there's let's say one day that just is out there and you need to find all the vulnerable contracts really fast. So that's an ideal, let's say, tool for this kind of situations. Thank you all. As I said, there's still plenty of stuff that you can research. A lot of stuff that our team or people who do have access to the mainnets, they didn't start researching yet some attack vectors and etc. If you feel that you want to be helpful for the projects and also to get some payouts, whatever, if you're a white hat, please feel free to ping me on Twitter at Cameo with the 3 instead of E. And I'll try to get you mainnet accesses. So the thing is that just a couple of words on that side. So it's the tool is free. Okay, so we're not charging for anything, but the access to the mainnets is gated. So you need to, so you can register and play with the testnet, but if you want to run queries on Ethereum mainnet and some other mainnet chains that we have integrated, you need to pass, let's say, a due diligence, so we can understand that you're not from North Korea or something, that you're a white hat, and we will grant you the access. Okay, thank you so much.